Howdy, I'm the amateur logician. Let's continue our studies in propositional logic, and to this end we will look at part of section 2.5, further rules of inference. We're using the old textbook, First Course in Mathematical Logic. In this video we'll cover such things as the law of addition, the hypothetical syllogism, and what's commonly known as a constructive dilemma. Now I should make a warning here. Unfortunately, what most textbooks call the constructive dilemma, the Suppes and Hill textbook calls a disjunctive syllogism. But even more confusing than that, when other textbooks use the term disjunctive syllogism, they're referring to something totally different than what the Suppes and Hill textbook refers to. And so, because that's so confusing, it will confuse everyone, it will confuse me, I will stick to the standard terminology and just call it a constructive dilemma. But in any case, let's get started. Alright, as I said, we're going to be covering things like the law of addition, the hypothetical syllogism, what most textbooks call the constructive dilemma, but also such things as the so-called tautology, the commutative laws, and De Morgan's laws. Most textbooks abbreviate the law of addition as ADD. The Suppes and Hill textbook abbreviates it as LA. But either way, in the law of addition, we have a single premise such as P, and then from that we can conclude that P or Q must be the case. The reasoning is simple, because in a disjunction, at least one option must be true. But the premise 1 tells us that P is true, and so we can put it in a disjunctive relationship with Q, regardless if Q is true or if it is false. Because we do know P is true, and so this molecular sentence, P or Q, must be true. It must follow from the premise P. What about the hypothetical syllogism, HS for short? Here we have something like this. First premise, if A, then B. Second premise, if B, then C. Conclusion, therefore, if A, then C. There's a chain reaction, because if A is the case, then B will be the case. But if B is the case, C must be the case. Hence, if A, then C. We have that chain reaction. For what we will be calling a constructive dilemma, CD, we have something like this. First premise, if P, then Q. Second premise, if A, then B. Third premise, P or A. And then we can conclude that therefore Q or B. Because our third premise is a disjunction, we know P must be the case or A must be the case, or both of them might be the case. But if P is the case, Q must be the case. If A is the case, B must be the case. And so we have the disjunction Q or B. With the tautology, T-A-U-T, we have simply P or P as our premise, and obviously from that we can say P must be the case. P is the case or P is the case, therefore P must be the case. We've already covered the commutative rules or commutative laws, C-O-M-M, but to review, for example, if we have A and B, from that we can get, therefore, B and A. The order doesn't matter. Likewise, if we had A or B, well, therefore, B or A. Why is this important? Besides just saying that this statement here and this statement are logically equivalent, you have to remember that in a lot of textbooks, if you do simplification, you could only simplify the very first term. So if you're given A and B, you can simplify it to just get A by itself, but you couldn't get B by itself. You would have to first do the commutative rule, and then when you do that, you can get that B by itself through simplification. So that's one reason, besides just knowing that these two statements are equivalent. And as far as De Morgan's law goes, DM, I'm actually going to cover that in the next video. With the help of the Suppes and Hill textbook, let's put a little meat on the law of addition. Recall that, given a true sentence, we can put it into a disjunction with any other sentence, which itself can be true or false. If we're given the premise P, we can conclude that P or Q is the case. That's a good argument. It is valid. This works because in a disjunction, at least one option must be true. Both options can be true, but it's not necessary. On page 80, we're given the example, this book is blue, and that's true. Conclusion, either this book is blue or it is red, B or R. Given that B is true, it must be the case that B or R is true. Likewise, we can conclude either this book is blue or it is new, B or N. Well, given that B is true, B or N must also be true. Since this exercise is pretty easy, I don't want to dwell on it too long. We should move on to more interesting, more challenging exercises. Nevertheless, I want to point out a few things. The question is, are the arguments valid or invalid? For example, the first two arguments clearly are valid. Even the second argument is valid. We have the premise Q. We conclude, therefore, Q or not R. Since Q is true, regardless of the truth or otherwise and not R, we're good to go. So that's good. The argument number 3 is a little bit more interesting. We have first premise P, second premise, if P or Q then R, conclusion therefore R. We can see this is valid if we complete this argument and say for line 3, P or Q, using the addition law with line 1. So we're given P as the case for premise 1. We can put it in a disjunction with Q, and that's true. And because we could affirm P or Q is the case, we could affirm the antecedent to get the consequent. And so for line 4, we can say therefore R by modus ponens with lines 2 and 3. It's a good argument. On the other hand, for example, argument 9 is clearly invalid. We can't get P and not Q from the premise P. The addition law only works with disjunctions. Also, argument 10, for example, is clearly invalid. There's no way we can get a T out of that. The only way to affirm this antecedent is to have S being the case, but we're not told that, so it's definitely invalid. There's no way we can pull out a T. I now want to work on number 9 from part D of exercise 11. Like anything, to get good at these things, you need to practice. But here's a good example. We want to prove the disjunction y is less than 3 or x is greater than 5, and we're given 4 premises. The first thing we should do is look for anything that's declared absolutely categorically to be the case. And in premise 1, we do have a conjunction. We have an and sentential connective. Y is less than 4, and x is equal to y plus 3. Then the question is there any overlap? We do see that it is not the case that x does not equal y plus 3. So there's the overlap. We're going to want to do a modus ponens inference eventually. And so for line 5, let's first say that x is equal to, actually let me move it up here. For line 5, we'll start by saying that x is equal to y plus 3 and y is less than 4 by the commutative rule with line 1. And then for line 6, we can get x is equal to y plus 3 by the simplification of line 5. If we double negate that, we could affirm this antecedent. Hence for line 7, we'll say it is not the case that x does not equal y plus 3 by the double negation of line 6. And then for 8, because this antecedent is in fact the case, the consequent follows. So x is greater than 2 by modus ponens with lines 2 and 7. Notice that this statement contradicts this statement. So we should be able to eventually do a modus tollens inference. So for 9, we should double negate. That way we can deny this consequent to deny the antecedent. So we'll say it's not the case that x is not greater than 2, double negation, line 8. And then for 10, we can get it is not the case that y is not greater than 2 by modus tollens with lines 3 and 9. For line 11, let's double negate y is greater than 2 by double negation of line 10. So we move from here to here. Line 11, y is greater than 2, appears in line 4. It is a conditional overall, but to affirm that we also need it in a disjunctive relationship. And so for line 12, we can say y is greater than 2 or y is equal to 3 by the law of addition with 11. Because this is true, we can put it in disjunction with anything. And now we could affirm that antecedent. So for line 13, we can say x is greater than 5 by modus ponens with lines 4 and 12. So we're almost there. We want to prove this disjunction. We have x is greater than 5. So for 14, let's just say x is greater than 5 or y is less than 3 by the law of addition, line 13. And then for 15, we can conclude that therefore y is less than 3 or x is greater than 5 by the commutative rule 14. And that concludes that proof. Let's consider the law of hypothetical syllogism, or HS for short. Thankfully, if you pick up any textbook on logic, there's no ambiguity here in terms of terminology. The hypothetical syllogism is a hypothetical syllogism. Now we can derive a conditional sentence insofar as one conditional premises consequent is another conditional premises antecedent. I think an example will help. This is from page 83 of the Suppes and Hill textbook. If the day is warm, then Judy goes swimming. W implies S. Second premise, if Judy goes swimming, then she does her homework after dinner. S implies H. Conclusion, therefore, if the day is warm, then she does her homework after dinner. W implies H. And there's a chain reaction. If W, then S, but if S, then H, so if W, then H. Now, unlike a modus ponens inference, nothing is being affirmed. There are only conditional or hypothetical propositions here. And we can just appeal to our intuition to see that this is a valid argument, a valid inference. Please remember, when it comes to these formal mathematical proofs, these have the same exact structure or form as an argument such as if P, then Q, not Q, therefore not P by modus tollens. It's just that P might be an equation instead, such as y plus z is equal to 8. The same exact rules of inference apply here. And with that in mind, let's look at number 9 and prove y plus z is equal to 8, given our 4 premises. Note that they're all conditionals. We have this arrow. So now the question is, do we have any overlap? And we do. We have this xy is equal to 6 as a consequent, and here as an antecedent. This means we have a hypothetical syllogism. We can say for line 5 that if xy plus z is equal to 11, then x is equal to 2. Because if this is the case, then this will be the case. But necessarily, if that's the case, this will be the case. But now notice that that appears exactly as an antecedent. And this statement here, so the hypothetical syllogism with lines 3 and 4, is affirming that this in fact is the case. So we could affirm this antecedent to affirm this consequent. So for line 6, we can say y is equal to 3 and z is equal to 5 by modus ponens with lines 2 and 5. We have the z is equal to 5, and it appears as the antecedent to a conditional. So for line 7, we'll say z is equal to 5 and y is equal to 3 by the commutative rule on line 6. And then for 8, we'll simplify to get z is equal to 5. Simplification, 7. Then we could affirm the antecedent to get the consequent there. So for 9, we can get y is equal to 3, arrow, y plus z is equal to 8, and z is greater than y by modus ponens with lines 1 and 8. We ultimately want to prove this statement here, so I think we should simplify because we have a conjunction on line 9. So for 10, we can get y is equal to 3 implies y plus z is equal to 8 by the simplification of 9. The antecedent y is equal to 3 appears here, line 6, and it's in a conjunction, so for 11, we can simplify to get y is equal to 3 by the simplification of 6. And then for 12, it does follow, therefore, y plus z is equal to 8 by modus ponens with lines 10 and 11. For number 10, we want to prove a conditional. If x plus z is equal to 3, then y is equal to 3. We're given 3 premises, and let's see what we have here. We have a disjunction, a conjunction. We're told that z is equal to 1, and that contradicts this statement, z does not equal 1. Hence, eventually, we want a disjunctive syllogism. So for line 4, we will say z is equal to 1 and x plus y does not equal 5. But the commutative rule, line 3, for 5, we get z is equal to 1 by itself by the simplification of line 4. Then for 6, we can double negate, so it's not the case, parentheses, that z does not equal 1, double negation, line 5. And so we're denying this, and so we could affirm this, line 7. We have a conditional, x plus z is equal to 3 implies x plus y is equal to 5. Disjunctive syllogism, 2, 6. Now notice that line 3 we have this x plus y does not equal 5. That contradicts this claim here, and that is a consequent to a conditional. So for line 8, we can simplify. We can get x plus y does not equal 5. So simplification, line 3. And then because this denies this, for line 9, we can say x plus z does not equal 3 by modus tollens with lines 7 and 8. Now notice that this statement here goes against this statement here in a disjunction, because textbooks, at least some textbooks, are very fussy. Let's first do the commutative rule. For 10, we'll say x plus z equals 3, or parentheses, x plus y is equal to 5 implies y is equal to 3. Commutative rule, line 1. And because then we can deny this, for 11, by our disjunctive syllogism, we can get if x plus y is equal to 5, then y is equal to 3. Disjunctive syllogism, lines 9 and 10. And if you look carefully, we have a hypothetical syllogism here. So look at lines 7 and 11. So we have this x plus y is equal to 3. If that's the case, then this is the case. But if that's the case, this will be the case. Line 12, therefore, if x plus z is equal to 3, this right here, then y is equal to 3, this right here, by our hypothetical syllogism with lines 7 and 11. Let's consider the constructive dilemma, or CD for short, in abstract general terms, and then, which will be more helpful, a concrete example. Given 3 premises, 1 disjunction, and 2 conditionals, we may be able to derive a disjunctive sentence. The disjunction's 2 disjuncts will be of the 2 conditionals antecedents. This allows us to infer a disjunction with the 2 disjuncts being of the 2 conditionals consequence. And here is the example on page 88 of the Suppes and Hill textbook. Premise 1, either it is raining or the field is dry. Second premise, if it is raining, then we will play indoors. If R, then I. Third premise, if the field is dry, then we will play baseball. Conclusion, therefore, we will either play indoors or we will play baseball. So I or B. As you can see, we have a disjunction, we have 2 conditionals. Since this disjunction is the case, it must be that I or B is the case, given these 2 conditionals. Turning to page 90 of the Suppes and Hill textbook, let's now work on 2 problems, number 4 and number 5. Number 4, we want to prove that S is the case given 4 premises. Premise 3 tells us that R is the case, and R happens to contradict not R, and not R is a consequent to a conditional. And so for line 5, we'll double negate. We'll say not R by the double negation of line 3, and then we can deny this consequent to thereby deny this antecedent. Line 6, not Q by modus tollens, lines 2 and 5. However, not Q allows us to deny this consequent to thereby deny this antecedent. So for 7, we can say not P by modus tollens, lines 1 and 6. Line 4 is a disjunction. P is not the case, so therefore T and S must be the case. For line 8, we'll say T and S by our disjunctive syllogism, lines 4 and 7. We want to prove S, and S appears here. For line 9, we'll say S and T by the commutative rule, line 8. And then for 10, we can simplify this first term to get S, simplification 9. For number 5, we want to prove a conjunction, not T and not P. So let's see what we have here. We are told that not P is the case right over here, but notice that we have this not S or not R. One of those has to be true, at least one of those, but if not R happens to be true, then that will apply not T. If not S happens to be true, that will imply P. So we can say not T or P because we have a constructive dilemma. Line 5, not T or P by constructive dilemma, lines 1, 2, and 3. For line 6, we could say P or not T by the commutative rule on line 5, but we're told that not P is the case. So for 7, we can get not T by our disjunctive syllogism with lines 4 and 6. Because P is not the case, not T must be the case. Well, now we have this not T, we have this not P up here, so let's just combine. So for 8, it does follow that not T and not P by the conjunction of lines 4 and 7. The Suppes and Hill textbook then goes into what they call a disjunctive simplification. Most textbooks call this a tautology. That's T-A-U-T for short. Here's an example from page 92 of the textbook. First premise, the Giants will win, or the Giants will win. We have a disjunction. Conclusion, therefore, the Giants will win. Now clearly, the so-called disjunctive simplification is more limited than the so-called conjunctive simplification. If we have A and B, we have a conjunction, and we can always simplify to get A no matter what this sentence is or this sentence. Whereas we can only get that G out of that disjunction insofar as this sentence is identical with this sentence. And finally, let's look at 3 more problems from part C of exercise 15. Number 1, we want to prove the conjunction S and Q. We have 3 premises. The second premise denies T. T is not the case. T happens to appear in disjunction, and so through a disjunctive syllogism we can get P. The Suppes and Hill textbook will allow us to do that. However, some textbooks you can only deny the first sentence of a disjunction. And because T is not the first sentence, we have to first resort to the commutative rule. That is to say, for line 4, we would say T or P by the commutative rule, line 1, and then with this not T, we can deny that to get P. So for 5, we'll get P to the disjunctive syllogism with lines 2 and 4. Note that P pairs in the antecedent to a conditional, so we could affirm that to affirm that consequent. For 6, Q and S by modus ponens, lines 3 and 5. We have Q and S, but we want S and Q. So to justify that, we have to say we're using the commutative rule. Therefore, it follows S and Q by the commutative rule, line 6. For number 2, we want to prove not parentheses R and not T, close parentheses. Let's see. Premise 3, we have a conjunction P and Q, and P happens to appear in the antecedent to a conditional. So for line 4, let's get P by the simplification of line 3, and then we could affirm the antecedent to get the consequent. So for 5, we'll get S, modus ponens, lines 2 and 4. S is here, not S is there, as the consequent of a conditional. So let's double negate. For line 6, we can say it's not the case, that is not the case, S, double negation 5, and now we can deny that consequent to thereby deny the antecedent. For 7, we can say it's not the case that parentheses R and not T by modus tollens with lines 1 and 6. For number 3, we have the conjunction S and R, and we're given 4 premises. We want to prove S and R. We have a disjunction, conditional, conditional, disjunction. But notice that this disjunction, Q or T, that is true. Q or T is true, it's a given premise. And so, at least one of those options has to be true. But if Q happened to be true, then not P would be true. Or, if T happened to be true, then not P would be true. We have a constructive dilemma. Line 5, we have not P or not P by a constructive dilemma with lines 2, 3, and 4. In here, this is just a tautology. So for 6, we can get not P by the tautology rule, line 5. We have a disjunction for our first premise. For 7, we'll say P or parentheses R and S, close parentheses, commutative rule, line 1. We can deny this and then affirm this. So for 8, we can get R and S, disjunctive syllogism, line 6 and 7. We want to prove S and R. We have R and S, so for 9, we can justify S and R through the commutative rule, and we're using line 8. I must admit that the level of difficulty with some of these problems was a little bit uneven, especially for those more mathematical arguments. But I hope if you're a beginner, you nevertheless understood what was going on and learned something. But we'll continue this. We'll finish up section 2.5 in the next video. I hope to see you then. Bye for now.